In this project, we explore using contraction metrics-based stability analysis for nonlinear system via SOS programming. Contraction analysis provides an alternative perspective into stability in terms of convergence of arbitrary trajectories. It's stronger than Lyapunov stability, independent of initial conditions, and it's shown that it's easier to analyze stability under uncertainty in this framework. The key idea is we investigate incremental stability between arbitrary trajectories. If we can find a minimum length path called geodesic connecting two trajectories at every time instant and show that this path length is shrinking over time, then two trajectories converges. Specifically, the path length is defined as the integral of the norm of every differential element under a specific metric m. So then the question is, how do we find an m that guarantees the path length is decreasing over time? For a general nonlinear system, the differential element of the path connecting two trajectories follows its differential dynamics. If the length of a differential element delta x, m delta x, is decreasing over time, then equivalently we can have a linear matrix inequality condition S1. Similarly, if the length is decreasing exponentially with rate lambda, we have 2 as a condition. Condition 1 and 2 provide stability in terms of asymptotic or exponential convergence to a single trajectory. To certify LMI conditions, we want to make sure a matrix is positive definite. This can be achieved by the notion of matrix SOS. Given a vector indeterminate y, S is a SumofSquares matrix if the scalar polynomial y transpose sy is SOS polynomial. Therefore, searching for a positive definite M and a negative definite R can be formulated into a standard SOS program. In implementation, we search for polynomial entries for the metric matrix M. Let's consider a simple stable linear system. On the left phase plot, the black line and red line are two trajectories of the system, where the blue lines represent the connecting paths in between at the same time instant. Because linear system always has constant contraction metric, the connecting geodesics are always straight lines. On the right figure, it shows that the path length is indeed exponentially decaying over time. Note that for linear systems, the existence of a contraction metric is both sufficient and necessary for stability. For nonlinear system, the stability analysis becomes more interesting yet more challenging because the matrix Mx now is spatially varying. To compute geodesic, which is the minimum length path connecting two trajectories, we need to first approximate the length integral with summation and then solve a non-convex optimization problem. Because non-convex optimization does not guarantee a global minimum solution, finding a geodesic could be challenging, as shown in the figure as an example. If we can find accurate representation of geodesics, that would enable us to do fast online trajectory stabilization through an extension to control contraction metrics. Thanks for allowing me to share my enthusiasm about this contraction analysis approach to stability. I hope you might find it interesting.